Here we'll talk about how to handle systems that have an infinite number of solutions. In this system, once again, let's begin by looking for any single letters and trying to solve for them. You can see in line 1 that we have all single letters. We have x plus y plus z equals 7. So, since there are all single letters in line 1, we could solve for any letter we like. I'm going to pick x for the letter I'll solve for, but really it won't make much difference. Therefore, in line 1, I'm going to box in this x and tell myself I'm going to solve for it, and that means that the y and the z will have to move to the other side. Therefore, my new line 1 will consist of x equals 7 minus y minus z. Now that I know this, I can replace x in both of my other equations with that 7 minus y minus z. First, I'll write my new line 2. Line 2 was 3x minus 2y minus z, but now I'm going to replace that x. The x is going to be replaced by 7 minus y minus z. I'll do the same thing with line 3 now. Line 3 was x plus 6y plus 5z equals 24, but I now replace that x with 7 minus y minus z also. Now, on line 2, I will distribute the 3 to this parentheses. 3 times 7 gives 21, 3 times negative y gives negative 3y, 3 times negative z gives negative 3z, the negative 2y and the minus z are still present, and we'll set this equal to 4. You'll notice that we have a constant on the left here. We'll have 21, which we have to move to the other side. When we move it, the 21 will become negative 21. We'll now have 4 minus 21 is negative 17 on the right side, and we will still have negative 3y minus 3z minus 2y minus z on the left. Now let's combine any of the variable terms. We have negative 3y and negative 2y. Those will combine and make negative 5y. We also have negative 3z and negative 1z. Recall that if you have negative of a letter, we'll write the invisible 1 in there. And so negative 3 minus 1 gives negative 4z. And we'll say this equals negative 17, and this will be our new line 2. Now we'll repeat this same process with our new line 3 here on the right side. We do have a 7 on the left. That's a constant, so that will have to move. The 7 will become negative 7 when we move it, and 24 minus 7 gives us positive 17. Then we will combine any terms that we can. I'll circle the y terms in green and the z terms in orange. If we combine the y's together, 6y minus y gives 5y. And the negative z plus 5z gives positive 4z. And this will equal 17, and that will be our new line 3. Now we'll take both of these new lines to our next page and see if we can solve them as a system. In this new system, since we don't have any single letters, let's think about the elimination method. However, in this system, you may notice that the y terms are exact opposites. Line 2 has negative 5y, and line 3 has positive 5y. Because the y terms are already opposites, we can simply add the lines together and expect y to cancel. The negative 5y plus 5y will cancel out, and also the negative 4z and positive 4z will cancel as well. But also notice on the right side, negative 17 plus 17 will also cancel. And so everything will cancel in this equation. Since everything is canceled out, we now have the equation 0 equals 0. 0 equals 0 is something that's called an identity. Anytime you solve a system and end up with an identity, that means that the system has infinite solutions. A system with infinite solutions is also sometimes called a dependent system. When you have a dependent system, The way we'll handle it is we'll let z stay as a letter because z can be anything. To show this, we will write z equals z. This means no matter what z is, we'll still have a solution to the system. So since we can't say what z is because any z will work, what we'll do instead is now try to solve for the other letters. When we solve for the other letters, it's okay to use z in our answer. So what we'll do is go to our new line 3 and recall line 3 said that 5y plus 4z equals 17. Now, since we can't solve for z, we'll solve for y instead. This 4z that's on the left we will have to move to the right. When we move it, it will become negative 4z. This will leave us with 5y equals 17 minus 4z. Now we can divide all of the terms by 5. When we divide all of the terms by 5, we'll just get a lot of fractions. It won't be pretty, but that's okay. We'll end up with y equals 17 over 5 minus 4/5 z. This will be our solution for y. Now that we have our solution for y, let's go back to the beginning. On the previous slide, we said for our new line 1 that x equaled 7 minus y minus z. I'll circle that in yellow now. Now that we know y, we can find what x is using this expression we wrote at the beginning. On this slide, I've copied our x from before and the y we just found. Now we're going to replace the y in our old equation with the new y we found. We'll place this set of fractions in for y. When we do so, we will have x equals 7 minus 17 over 5 minus 4/5 z minus z. We will distribute this negative sign on the outside to both terms inside. When we do so, we will have 7 minus 17/5 plus 4/5 z minus z. Then we will combine our constant terms and combine our z terms. If we take 7 minus 17/5, we will get x equals 18/5. Now we'll deal with our z terms. We'll take 4/5 z minus z and end up with negative 1/5 z. This will be our solution for x. So when we write our answer, we'll write in the triangular brackets, first the x, 18 over 5 minus 1/5 z, comma, 17 over 5 minus 4/5 z, and then for our z, we don't know what it is because it can be anything, so we'll just say z in the final slot. This will be your solution for when you have a system that's dependent. Thank you for watching, and we'll see you again